Hey everybody, Mr. Judson here. So we're going to take a huge jump today, not a difficult jump, but a huge jump in the amount of material that we're going to look at. And my goal here is to kind of take some things that maybe we don't really have to be able to do and sort of push that to the side, but not lose the meaning of it. We still want to kind of understand how things tie together, okay? So one of the things we've been talking about is, and these are both the same function, okay? I'm trying to find the area from A to B on both of these. And what we've talked about is using the idea of rectangles to find that area. And you know, if I was to do left sums, so I'll make the left side of the rectangle touch the curve. Let's say I've got a rectangle right here, and then I've got one right here, and then right here, and so on. And we can see here that we're not really getting the right answer because I missed some area here, but I added a bunch of extra area over here on this part. So how do I fix that so I'm not adding so much area or missing area? Well, the answer is you let the width of your rectangle get smaller. So maybe I come over here and I'm doing this rectangle, and then this rectangle, and then that one, and then that one. And what you can see is, okay, I'm still getting a little extra area here, but I'm not getting as much extra area. These are really bad rectangles. I'm not getting as much extra area as I got over here. But I still got too much, right? So how do I fix that? Well, I let the width get even smaller and smaller. Probably taking a limit as the width of each rectangle approaches what? 0, right? And so what I really want to do here is I want to do a summation for, let's just say, I equals 1 to n, where n is the number of rectangles that I'm trying to add up. And I'm going to do a whole bunch of, you know, length times widths over here. And what I really want to do is I want to do the limit as the number of rectangles approaches infinity. If the number of rectangles approach infinity, then the width is getting close to 0, right? And the more rectangles you have, the better your answer becomes. Now, if we were doing everything the way we were supposed to, we would now tackle this issue. We would add up an infinite number of rectangles. It's a bit of a mess. We could do it, but it takes us about 4 days to get through that. And when we're so short on days as it is, you know, we've got to find a place to cut some things out. I hate cutting this out because I love doing this. I think it's cool to see how when you add all these rectangles together, it eventually equals an integral of f of x dx. And we kind of see how that happens. So what we really want to get from this is we want to understand this idea that when you do an integral, you're really adding a whole bunch of length times width, so rectangles. We're adding a bunch of area of rectangles, so many that we're calling the number of rectangles almost infinity, which means that this little bit that we're off by here, those rectangles are so narrow that you can't even see that. And it becomes a perfect answer. So that's really what an integral does for us. But here's the new part. What we're doing now is we're saying that we're going to do the integral from A to B, and so we're going to put some numbers onto that integral. We're going to attach them there. And once we do that, that's called a definite integral. It has definite boundaries. everything that we've done so far is called an indefinite integral. There are no boundaries to it. We're just trying to figure out an expression that represents the area once we know what A and B are. Okay? So that leads us to what we call the fundamental theorem of calculus, which says this. This is kind of interesting because, you know, when you say fundamental theorem of calculus, it's kind of like, this is the big idea. This is it right here, you guys. How can we be hitting the big idea already this early in this semester? Well, we are, but we're going to do a lot of work with this throughout the semester, okay? So the fundamental theorem of calculus tells us this. When you do the integral of f of x dx, so the integral from a to b, this is little f. So little f is the derivative of f of x, big F of x, okay? So that's why you see the lowercase and then the uppercase letter here. So once I do the integral, right, this is the derivative, so if I go this way I'm doing the integral, then what I'm going to do is I'm going to take the top number, plug it into that function, see what I get, some number, minus what I get when I plug the bottom number in. And that's what we want to be able to do, is to evaluate definite integrals. That's our goal for today. All right, let's do an example. All right, so now, you know, just because we're saying that this is the big idea, doesn't mean this is hard. This is actually a pretty easy problem. I'm doing the integral from -2 to +2 of x squared minus 3 dx. Now, this right here is just an integral problem, all right? We're just answering an integral. There's a difference between that and finding the area between the curve. And today, we're just evaluating an integral. So when I do an integral, I add 1 to the exponent, divide by the new exponent. This will be a -3x. And I'll do this one time, but I won't do this on any other problems. Normally we write in plus c, and then what we do is we evaluate this from -2 to 2. Okay? So whatever these boundaries are, we just write those next to the bracket right here. So I'm going to plug in the top number first. So when I do that, I get 2 cubed, that's 8 thirds. Put a 2 here, I get -6. I don't know what c is, so I'll do that. And then remember in our theorem here, it's minus f of a. Minus everything you get when you plug that in. So minus, and now I'm going to plug a -2 in. So when I cube that, I get -8 over 3. I'll put a -2 here. -3 times a -2, that's a +6. And then plus c. And then what I need to do is I need to distribute that negative sign. So I get 8 thirds minus 6 plus c. Here I have to distribute that negative sign to all three of these terms. So this will become a positive 8 thirds. This will become minus 6. And that'll become minus c. Now, because both of those c's came from this variable right here, it means those actually are the same numbers. It's just one's positive and one's negative. And so they're going to add up to 0. And that's why normally with a definite integral, when we have these boundaries on here, most people just don't even write the c down, that constant. They just leave it off because it's going to cancel out anyway. And so I'll leave that off for all the future problems that we do that are definite integrals. If these boundaries aren't here, then it's an indefinite integral. Then you have to put the c in. Okay? All right, so let's see. I've got 8 plus 8, that's 16 thirds, minus 12. And so if I change that to a common denominator, I'll just multiply top and bottom by 3. So what I'm going to get is 16 minus 36. That would be a -20 thirds. Okay, and I would just stop right there. That's my, my answer to that integral. Now, it's not area, right, because there's no such thing as negative area. If they were asking us to find the area and I was using an integral to do that, I would need to look a little closer at this. Okay, but we're not worried about that right now. All we're focused on is just evaluate the integral. All right, so that is my answer. All right, let's do another one. All right, so you guys see if you can evaluate this integral. And just to make sure that we understand, like what I just said, we're going to use integrals to find the area, but I don't want to think area unless the question says find the area, okay? If I just say evaluate this integral, we're not thinking area at all. We're just thinking do the fundamental theorem of calculus and get a numeric answer at the end. All right, you guys go ahead and try it. All right, so the first thing I want to do is I just want to rewrite this. But we had a rule that says you can move a constant to the outside if you want. You don't have to, but if you want to, you could. So 3 times the integral from 1 to 4, and I'm going to write that as x to the 1/2 dx. All right, so now I need to add 1 to the exponent, so that's going to be x to the 3/2. When I divide by 3/2, I got to multiply by the reciprocal, and I'm going to evaluate that from 1 to 4. Still have a 3 on the outside. Notice how I didn't write down the plus c? Definite integral, we don't need to do that. So now I'll plug in a 4, so I've got 3 times. If I put a 4 in here, I've got 2 times 4 to the 3/2 over 3, minus what I get when I plug the bottom number in. So 2 times 1 to the 3/2 over 3. So let's see if this 2 means do the square root of 4, so that's 2. Cube it, you get 8. Times 2, that would be 16. So 16 thirds minus 1 raised to any exponent is just 1. Times 2, that's 2, so I get 2 thirds. Do what's inside parentheses first. I'm going to get 14 thirds. That 3 will cancel with that 3, and so my answer is 14. There's the answer to that integral. Let's try another one. All right, let's try this one. Yeah, I'll throw a little bit of trig in here as well. Okay, you guys give it a shot. All right, so when I look at this, I just think, okay, the integral of a secant squared. What did I take the derivative of to get to this? Derivative of a tangent. That would give me a secant squared. So the integral of a secant squared is a tangent of x, and we have to evaluate this from 0 to pi over 4. All right, so that means I plug this number in first, this one second, and I subtract those. So what I have is a tangent of pi over 4 minus a tangent of 0. So now I got to think unit circle. Pi over 4 is right there. I know that's the point root 2 over 2 comma root 2 over 2. This is the point 1 comma 0. So if I do the tangent of pi over 4, I'm doing sine over cosine. So same thing top and bottom, that's 1. Minus what I get at when I do the tangent of 0. So if I do sine over cosine, I've got 0 over 1, which is 0. And so my answer to that integral is 1. All right, one last problem. All right, so we've got the integral from 1 to 4 of x minus 2 over the square root of x dx. You guys go ahead and try it. All right, so first thing, if anyone's looking at this going, okay, I'm going to move that 2 to the outside, that only happens when you're multiplying by a number, okay? Our rule said this: if you have an integral of a constant k times f of x dx, that equals k times the integral of f of x dx. So I have to be multiplying, okay? It can't be adding or subtracting and do that. So I do think what I would do with this problem is I would divide this up into 2 different fractions. So the integral from 1 to 4, I've got x over, we'll call that x to the 1/2, minus 2 over x to the 1/2. And then when I divide these, I subtract the exponents. So 1 minus 1/2 is 1/2. So that's the integral from 1 to 4 of x to the 1/2 minus 2, we'll just bring this up and call it a negative exponent. See, I have to get this to the point where I have a variable raised to an exponent. I don't care if the exponent's positive or negative, decimal, fraction, whatever, but it's got to be a variable raised to an exponent, or a number times a variable raised to an exponent. Then I can do the integral. Okay? So I want to add 1 to the exponent and divide by the new exponent. So that means this will become x to the 3/2. If I divide by 3/2, I got to flip it over and multiply by 2/3. Minus, I'll have 2x. Add 1 to that, you get to the 1/2. Divided by 1/2, that means I got to flip it over and multiply by 2 over 1. And evaluate this from 1 to 4. All right, so if I put a 4 in here, again, that's the square root of 4, which is 2, raised to the 3rd power, that's 8, times 2, that's 16/3. Minus, here I've got 4. If I put a 4 in here, I got the square root of 4, which is 2. 2 times 4, that would be 8 over 1, let's call it 8, minus what I get when I plug this 1 in. So plug a 1 in there, 1 raised to any exponent is just 1, times 2, that's 2, so 2 over 3. Minus, if I plug a 1 in here, I get 1, times 4, that's 4. And I just got to figure out what that answer is. So usually I'll do these 2 things first because there's a common denominator there. So 16/3 minus 2/3, that would be 14/3. And then I'll do a negative 8 plus 4. And now I'll think common denominator. So if I multiply top and bottom of this by 3, I've got 14 minus 12. So that would be 2/3. There's my answer. And I'm not putting square units down because nobody said anything about area. We're just evaluating an integral. So in the end, my answer is just some number. So one last thing to talk about. They're gonna ask us to verify that this is correct using our graphing calculator. So how do I do that? Let's go back to the original problem. All right, there it is. I'll pull up the graphing calculator. And if you look right there where the 7 is, that's our integral symbol. All right? So, back up here. So what I want to do is I want to do an integral. So secant, and then 7, there's the integral sign. I want to punch in my function. So what I have is, in parentheses, I've got x minus 2, close parenthesis, and then divide that by the square root of x. I got to put parentheses to make sure I'm dividing that entire numerator by the square root of x. So square root x, close off that. And then for the dx, we have to put comma x in there. Okay, that's the syntax. That means that needs to be there in order for an integral to happen on the calculator. And then where do you get these numbers? So if those numbers weren't there, I would just do a parenthesis and hit enter. Okay? But if there are numbers there, then I'm going to go comma 1, comma 4, and then in parentheses. So we're doing the integral of this expression with respect to x from 1 to 4. Okay? And what I'm expecting to see, I don't remember what we had for an answer. We'll check in a second. There it is, 2/3. Hopefully that's what I had. Make sure that the way this integral is written looks the same as what we have right here. That means I typed it in correctly. So 2/3 is our answer, and yeah, that's what we got. So I verified that I did that correctly. Okay? If we go back and look at the calculator, if I take off that 1 to 4, so let me just back up here, whoops, put the x back in. See, now it's just going to do the integral for me. So 2/3 x to the 3/2, that's what we got right here. And then minus 4 square root of x, that's what I have right here. Minus 4, when you multiply those, that exponent means square root. Okay? So we can do both indefinite and definite integrals on our calculator. We just use that integral symbol right there. So let's just write down that syntax real quick. So to do this on the calculator, we're going to do the integral, and then, whatever our function is, f of x, comma, with respect to x, comma, integral from a to b, and then a closed parenthesis. Now, if you do need to enclose your expression inside parentheses, well, then you've got another set of parentheses right there. Okay? But that's the syntax for doing this on the calculator. Let's just say that right there we get by doing secant and then the 7 button. Okay, there's a little integral symbol right there. All right, that's what we have for today, you guys. Let me get you a homework assignment. All right, so here's what we have for tonight. This is still assignment number 2, our second week of the new semester. This is Thursday's portion. We're doing page 292. We're going to do 5 to 23 odd. All right, you guys, you take care, stay safe. I will see you on Monday. All right, we'll see you.